In the 1950s, the first computer graphics were produced on small, circular screens of laboratory oscilloscopes. Today, that same field produces the photorealistic imagery used in modern simulations and cinema, capable of rendering millions of polygons in real time. Formally, computer graphics is the branch of computer science concerned with generating, manipulating, and representing pictorial data, images, animations, and video using a computer. We classify these systems by how much control the user has. Interactive graphics allow for two-way communication, like the real-time adjustments in CAD software or games. Passive graphics are a one-way street, where the user is only a spectator to pre-rendered sequences. Regardless of complexity or the level of interaction, every graphical output relies on a single process, the translation of mathematical models into physical light. This translation is managed by an overarching graphics system that moves data from a conceptual model to a physical display. A typical system has 5 components: input devices, a processing unit, graphics software, a memory layer, and a video display. This memory layer, the frame buffer, stores visual data in a grid format before it hits the screen. While the screen is the primary destination, the system can also route this data to hard copy devices, like printers, for a permanent record. Because the video display is the final point of the pipeline, its physical limitations dictated the evolution of the entire computer architecture. For decades, the hardware standard was the refresh cathode ray tube, or CRT, a device that defines the core mechanics of how images are drawn. Inside the CRT, a heated cathode emits a stream of electrons through a process called thermionic emission. A focusing system then takes that broad stream and narrows it into a sharply defined beam. To create an image, a magnetic deflection yoke uses fields to steer this beam horizontally and vertically, allowing it to strike any specific coordinate on the front of the screen. When those high-speed electrons hit the phosphor-coated screen, the phosphor emits a spot of light. This light is temporary. Persistence describes the short duration a phosphor glows after the electron beam moves away. Because the light decays so quickly, the system must redraw the entire image 60 or more times per second to prevent the viewer from seeing a flicker. This is known as the refresh rate. The maximum number of these distinct light points that can be plotted on the screen without overlapping defines the display's resolution. Early graphics engineering was a race against these physics, designing memory systems fast enough to refresh the image before the phosphor went dark. Moving from monochrome lines to full-color imagery required a way to manipulate the light at a microscopic level. Early vector monitors used a beam penetration method. By varying the voltage of the electron beam, the system could pierce different depths of the phosphor coating to produce a small range of colors. The shadow mask method eventually became the standard for raster displays because it allowed for a much broader color palette. The screen is coated in triads, groups of red, green, and blue phosphor dots. 3 separate electron beams pass through a metal shadow mask, which ensures each beam only impacts its corresponding color. By adjusting the intensity of these 3 beams, the system can produce the millions of color combinations necessary for photorealistic images. The specific method used to steer the electron beam determines how the computer's memory must be organized. In a random scan system, the beam acts like a pen, directed only to parts where a picture is drawn, tracing lines point to point. This relies on a display list, a set of line drawing commands in memory that the system re-executes with every refresh. This produces smooth, high-resolution outlines, making it the preferred choice for early engineering and architectural drawings. However, the refresh rate depends on the number of lines. If the image becomes too complex, the beam cannot finish the list fast enough, causing the display to flicker. In a raster scan system, the beam instead sweeps across the entire screen row by row, from top to bottom in a fixed pattern. Here, the memory uses a frame buffer to store an intensity value for every single pixel on the grid. The advantage is that the refresh rate is constant. Whether the screen is nearly empty or contains a complex, shaded scene, the beam always follows the same path at the same speed. The drawback is aliasing. Because the image is built from a discrete grid of pixels, diagonal lines often appear with jagged, stair-step edges. Because raster systems could handle visual complexity without losing their refresh rate, they became the universal architecture for modern computing. To manipulate these digital grids and vectors, humans use input devices to feed data back into the system. While a mouse handles 2D movement, 3D environments often require trackballs or spaceballs. A spaceball provides 6 degrees of freedom, allowing for simultaneous movement and rotation in 3 dimensions. Advanced training environments, such as flight simulators, combine these high-precision inputs with multi-panel raster displays to create immersive, interactive models. This architectural split between lines and grids also extends to hard-copy devices. Plotters move a physical pen to create precise, vector-based line drawings. Non-impact printers, like lasers and inkjets, operate on raster logic, building images out of a dense pattern of dots. From a mouse click to a stylus stroke, every input is eventually translated into the numerical coordinate data that the graphics pipeline requires. Managing millions of raw pixel values is impossible for a user, which necessitated the development of graphics software to bridge the gap between hardware and intent. This evolution moved from early systems like Ivan Sutherland's Sketchpad in the 60s to the 1980s, when personal computers like the Macintosh brought raster-based graphical interfaces to a mass audience. Today, we distinguish between low-level programming packages like OpenGL, which communicate directly with hardware, and special-purpose applications like Photoshop or AutoCAD, which provide tools for specific professional tasks. Even at the software level, the divide remains. Images are represented either as vector graphics, using mathematical geometric primitives, or as raster graphics, using a bitmap grid of pixels. From the first oscilloscope traces to contemporary VR headsets, the field remains a study in translation. Computer graphics is the rigorous architecture that turns mathematical coordinates into a structured grid of light.